Okay, welcome to our podcast series called Lime Time in Texas. And our next topic, the topic we're going to cover right now, is about misconceptions about lime. The most common one that I run into is people tend to say that lime leaches out. So I'm going to try to address that and talk just a little bit about some of the things that we see surrounded around that topic. So the most common misconception, and I hear it sometimes when I'm at conferences and things, they say, well, lime, we're afraid to use lime because it's susceptible to leaching out. In fact, some of our competitors will go saying that, hey, lime leaches out, don't use lime. They also say, well, lime's not permanent, so we want to, we hear that sometimes, another misconception, or that lime loses its effectiveness over time. So I'm going to try to address all of those particular things as we go throughout this little presentation here. So let's just talk about some facts surrounding lime. So when clay soil is stabilized with lime, it's actually virtually impossible for the lime to ever leach out. So if you use a clay soil and it's done properly, it will never leach out. Now, I will just say here that if you misapply lime, so for example, if you go apply lime to something like a very sandy soil that's very low PI, then it's not going to react with that soil. And so under certain circumstances, lime could leach out, but if you follow the design procedure, these would be situations where you should never be using lime anyway. But if you're using it in expansive clay soils, which is primarily what we're talking about here today, there's not an issue with it leaching out if you design it properly. So for more than 70 years in Texas, a couple of other facts, lime has been the most used additive, and it's the additive of choice for permanently stabilizing expansive clay soils. In fact, there's really not an alternative or a good alternative to lime when you're talking about expansive clay soils. It's proven to be the most durable option for treating clay soils, and if you look at any recommendations really throughout the United States and even in the world, people talk about on high PI clay soils, lime is going to be the stabilizer of choice. A few other facts about lime stabilization, soil stabilization with lime is that when lime is designed and constructed as specified, lime stabilized soils, there's a couple of things you should know about them. One, they'll start with a pH value of about 12.4, and that pH will remain at least above roughly 10.5 throughout the life of that subgrade. So 20 years, 50 years, 100 years down the line, you go check the pH of that soil, it's going to still be above 10.5. It'll also continue to gain strength throughout time, and that pozzolanic reaction that's happening in the soil will continue to happen as long as there's enough free calcium in there and moisture to keep that pH up and to continue that chemical reaction that happens. If you look at, this is a little slide I got from Tom Scullion from TTI doing some research on some projects in Texas, and this was just a particular ramp that he was looking at. So you start with an 8 KSI value for the clay soil that was there, the native clay soil. Once that was treated, that was increased up to 140 KSI over time. So I don't know the exact age of this particular pavement here, but you can see here the example of that lime doing what it's supposed to do, which is increase that strength significantly over time. We've talked about this slide before. I show it a number of times that what lime does, but I only want to focus on the red area here right now. It's when we talk about stabilizing a clay soil. So if you stabilize a clay soil, first of all, you need to do a lime series test, which we've talked about in previous podcasts, to get that pH up to 12.4 and make sure that you have enough lime in it to properly stabilize it. If you do that, the pH will never go below, or should never go below 10.5, so it will stay up in that range. Now, if you put a lesser amount of lime in there, you're going to do something what we call is modifying that clay soil. Modification starts to happen at about a pH of 10, and it will go up a little bit above 10.5. But over time, and it doesn't really show it on this graphic, over time that pH can actually go back down to 7. It's not a permanent solution. So if you put a little bit of lime into a clay soil, it's essentially going to get consumed, but it's not enough lime to keep that chemical reaction going throughout time. So that's kind of the main difference there. This is another slide that I show all the time, just showing that to get to solubilize the alumina and silica that's in a clay soil, which is really our goal. So to form a pozzolanic cement, you've got to make it soluble the silicon alumina. To do that, you've got to get the pH up at least to above 10 there. So again, our design procedure is to go all the way out to 12.4 here. But this is the main reason, is because you can't form a pozzolanic cement, which is what causes the permanent reaction in that the long-term strength in that soil, by forming the calcium silicate hydrate and the calcium aluminate hydrate. So again, to make that happen, you've got to get that pH up there above 10, 10.5, and maintain that over time. This is another slide I've shown many times. Again, this is the design, the Eads-Grimm or the lime series test is showing that to get up to 12.4, you have to add enough lime in there. And this also shows what happens when you don't get enough lime in there. So if you only put 2 or 3% lime in there, you may get the pH up initially. You may get a textural change, a breakdown in the gradation. You may see a PI reduction, but you're never getting to the point of forming long-term pozzolanic cements that are going to continue to gain strength over time. So really, this is our goal. Just looking at the picture, it's changing a bad soil into a good clay soil, a good soil that is a workable construction material after doing lime stabilization. I want to show some historical data here. This is some work that's done by Ruben Carrasco at TxDOT. So they went and they've looked at a number of pavements throughout Texas over the years, and when they're going in and doing forensic studies and just doing pavement evaluations. And what they see now, this particular project is in the Beaumont district of TxDOT. This was been down 61 years, so it's almost as old as I am. And what you see is the lime stabilized layer at the bottom of that. It actually does form and looks like a lean concrete underneath there. So when they take these cores out, many people often mistake this for thinking that that's an old concrete pavement or something underneath it. But that part at the very bottom is just the lime stabilized subgrade that was done 61 years ago. So that one was done in 1963. Here's just another example of what lime treated subgrade looks like. And this one is wet, so it's a little bit deceiving in the picture. But again, it comes out as a solid. It doesn't come out as a fine, friable material. It comes out looking like a solid, almost looks like just wet concrete there. But that one's 25 years old there. This was in the Houston district, done in 1999. Again, this was from Ruben Carrasco. And then here's another project that was done in Fort Worth, 1976. This is underneath the concrete pavement. This is, I believe, either the base material or some hot mix asphalt that was underneath there. But this is the lime-treated subgrade that was been down for 48 years. After 48 years, some interesting things happen. So if you look at the strength there, for one, it goes from a 10.6 KSI, which is a relatively weak subgrade, that's when it's untreated, to the part that's actually treated with lime has a 41 KSI. So 41 KSI is getting up to where it's very similar to what the base material or the granular base material would be. So it's got about 4 times more strength than what the native subgrade has there. The more interesting part about this is if you add a liquid called phenolphthalein, which changes colors. It changes from clear to this pinkish color if you have a high pH. So typically, and I've heard different numbers, but a pH of at least 9.3 will usually start to get a color indication. But after this has been down for 48 years, you'll still see there the evidence that the lime is still there, still working, and it's still changing colors. And so that's a pretty good indicator that, yeah, we've got lime in here, and this is evidence that it's doing what it's supposed to do. So one of the things I hear about people that say, well, we think the lime leached out, is because they'll go in with phenolphthalein, and if it doesn't change colors, they say, well, okay, it must have leached out because it's gone. Well, there's a couple of things can happen there, is that lime may have gotten consumed and there wasn't enough lime in there to really fully treat that and keep that chemical reaction going. And in that case, that pH is going to be up temporarily, and then it's going to drop back down. So it may be below 9.3. It's not going to be detectable with phenolphthalein. So that's one case that we have. But a lot of times that clay has just consumed that lime, and there just wasn't a high enough concentration in it to maintain that the pH above 10.5. So some common reasons that people say that lime leaches out, and I'll just kind of go through this list here, is that usually the amount of lime that it was added was insufficient to reach the pH of 12.4. So that happens a couple of ways. So for one, they may not have gone in and initially started and done a design, which is doing the lime series or the Eads-Grimm test procedure, and determining that this, for example, I'll give you the example, this may have needed 6% in this soil, a given soil, and you see some random guidelines sometimes it just says, oh, we're going to use 4% lime. Well, 4% lime is enough to modify that soil, but it's not enough to permanently stabilize it or get that pH up enough to continue that chemical reaction to form the hydrates, the calcium silicate hydrate, the calcium aluminate hydrate in there to form those pozzolanic cements. The other thing is maybe you did the design procedure right and said, okay, we need 6% lime in this soil here, but the amount of lime was insufficient to maintain that pH above 12.5 to be detected. And there's a couple of ways that happens. For one, if you take, let me give the example, if you're going to mix 6% lime and you're going to go 8 inches deep with it, well, if you go 8 inches deep, it's going to be 6% lime. But if you overmix the depth and you go 10 or 12 inches deep, then you've diluted that amount of lime, which effectively you've lowered that pH and stopped that chemical reaction from the permanent chemical reaction from continuing to happen over time. So you're not going to get that pozzolanic cement forming over time. So again, that happens a lot. We see, and the last bullet item here says when the right amount of lime was added, but it was just mixed deeper than the specified depth, that basically just dilutes that concentration. So that's kind of the ways that this typically happens, but the bottom line is that if you design it and construct it properly, it's virtually impossible for a lime to leach out of a clay soil because it's going to get strong attraction to that clay soil and that chemical reaction begins to happen immediately. So I say here, starting back with our initial slide, these misconceptions, in the vast majority of the cases, it's just simply not true that lime is susceptible to leaching out. It's not if it's done properly, and it is permanent if it's designed and constructed properly, and it will not lose its effectiveness over time. In fact, it becomes more effective over time, continues to gain strength. Thank you for watching this episode of our podcast. If you want to learn more about the use of lime, reach out to us on our website at limetexas.org. You can also email me at dalerand@limetexas.org. And please follow us on LinkedIn and subscribe to our YouTube channel. Thank you for watching.